types of rectifiers. So this is also I discussed in the last class, where I said that we have two types basically. One is half wave, the other one is a full wave. Okay, so half wave has a single diode, circuit connection wise, and the number of diodes used. And full wave rectifier has two categories in it. One is a center tapped full wave, and the other one is a bridge rectifier, where center tap full wave has two diodes and bridge rectifier has got four diodes. So the number of diodes that we are showing here as the difference among the rectifiers is one of the differences that we can consider. Okay, so now let us move on to the first one, which is called as a half wave rectifier. Okay, so we have the circuit diagram of a half wave rectifier. So how to draw the circuit diagram? So to draw the circuit diagram, you need to recollect the block diagram which I have discussed earlier. First we said that the first block is a transformer, right? Then the second block we drew is a rectifier. Then we have drawn a filter. And lastly, we talked about what?
Regulator.
Isn't it? We talked about a regulator. Now the output of the transformer is fed to rectifier, output of rectifier to filter, filter output to regulator. But as per our unit 2, we will be concentrating on rectifier and filter, because this already we discussed in unit 1. So no more we will be talking about this regulator part here. So now if we are starting our discussion with rectifier first, later on we discuss rectifier with filters concept. So whether it is a rectifier or a filter, okay, rectifier input is always given from a transformer, isn't it? So when you are saying the circuit of a rectifier always, okay, when you're saying or talking about the rectifier circuit, your circuit should consist of all the three blocks. Sorry, the two blocks. If it is with filter, this is added. But initially, we will be talking about only rectifier first. Then after studying in detail about rectifier, we will move on to adding filter to a rectifier, because filter is receiving its input as the output of a rectifier. So first we will discuss about the rectifier, then we move on to adding a filter to this. So if I want to draw the circuit diagram, my first component should be a transformer and second component should be the rectifier part. So what do I mean by rectifier here? I mean to say the component or device that we are using for rectification purpose. And what is the component or device that we are using for rectification purpose? It is nothing but the PN junction diode. So the circuit of any rectifier circuit will have first a transformer. Okay. And which type of transformer it is? Step down or step up?
Step down transformer.
Yes. So that is to be very much remembered. So we will be using a step down transformer. Then we use a PN junction diode. So the circuit of a half wave rectifier is like this. And the third important component we see is nothing but the load, because all the circuit or blocks which are connected or interlinked here, finally the output of all these blocks should be delivered to what? To an appliance, right? If it is a real time application or real time scenario, we need to give the final output to an appliance in real time. But since we are studying it theoretically here, you cannot go for any appliance to be connected. Instead, in place of an appliance, we go for placing a resistor, which we call it as the load resistance. So instead of taking an appliance, we connect it with a load, and that load we take is a resistor. So any electronic circuit, the end application should be tested theoretically or in the circuit with a resistive load. In real time, that resistive load gets converted to any one of the appliances that we are using at home. So which means to say the circuit of this rectifier should end with a load resistance RL. So these are the different components that you find in case of a rectifier. Now, if you talk about rectifier with a filter, what difference do you find? Rectifier with a filter?
Capacitor.
Yes, you get one more component added here, and that is nothing but we call it as a filter. So what are the different components that we use for a filter? It depends. Usually for a filter, we use R, L and C components either individually or in parallel, What is that? I repeat. Usually for a filter network, we don't say R because R we are showing it here as a load resistance. So we say it is simply L and C components we use either individually or in a combination. Okay, so your filter block consists of just these things: inductor, capacitor as a standalone or combination of this. So that gets added to a rectifier and the total circuit becomes what? Rectifier with filter. Rectifier with filter circuits if you add filter component in it. Fine. So this is how, based on the block diagram, you have to remember and then draw the circuit. Okay. So how do I have the circuit drawn for the first type of rectifier? Let us see. What is the first type of rectifier we said?
Half wave rectifier.
Half wave.
So it is half wave rectifier. So the first one we have is half wave rectifier. So why is it called half wave rectifier? That depends, or that can be understood when we try to study the operation of this rectifier. Okay, half wave rectifier. So first, anyone starts with the circuit diagram. So how do you have the circuit diagram for a half wave? What is the first block?
Transformer.
Transformer. So we don't show the block here. Instead, we show the circuit diagram. And already we said that it is a step down transformer. So the number of windings on the primary end will be less than the number of windings on the secondary. And whenever you draw a symbol of a transformer, there should be having a flux lines. Okay. So many people draw transformers in different ways. See, like this. So there is a lengthy gap between primary and secondary. It should not be the case. Okay, so the distance that you represent for primary and secondary, we should be in such a way that you can show the flux lines in between. Neither you cannot draw the transformer like this. Okay, and show the flux lines overwritten on it. This is also not correct. So give the gap in such a way that you can draw true flux lines in between the primary and the secondary windings. Clear? So with this as a transformer symbol, now what will be the next component that you can see?
Rectifier.
So
I mean,
rectifier uses what?
Diode, PN junction diode.
PN junction diode. So your PN junction diode gets connected like this. Now diode output is fed to what? To a load. What is the load we are taking here?
Resistor.
Resistance. So the resistor gets connected. So the other end of the resistor is connected to the secondary other end. So diode D, and this is the load resistance RL, and it is across this RL we measure the output voltage V0. And this is the secondary voltage, which we call it as V2. Some textbooks also say it is Vs. And this is where I have the primary voltage V1. Okay. And because of this primary voltage, you may see current I1 passing in the circuit. And because of V2, you may see current I2 entering in the secondary half of the circuit. Okay. So this is how you have the circuit diagram of a half wave rectifier: a step down transformer, a PN junction diode, and then the load resistance RL. Fine. So if this is how I have the circuit diagram, how do I study the operation of this particular circuit? So to study the operation of this particular circuit, again, you need to know what is the input at the primary, because the diode here is receiving input from the secondary, isn't it? But secondary is in line to the primary, which means whatever the primary voltage you are giving, that will be induced to the secondary, and secondary voltage will be fed to the diode. Based on the state of this diode on or off, the output voltage is observed. Okay. Based on the state of the diode on or off, the output voltage is observed. Fine. So now, what is the input that is available at V1? What is the input that is going to V2? And finally, what is the input that is received by the diode? This is what you need to know first. Now, already we know that primary of the transformer, it is connected to what? It is connected to AC mains. Isn't it? Primary of the transformer is always connected to AC mains. So what is the voltage that we receive from AC mains?
230 volts.
Yes, 230 volts. Amplitude is 230 volts. Frequency is 50 hertz. Very, very important. In objective questions, you will be expecting this. What is the frequency of the primary voltage? 50 hertz. What is the frequency of the secondary voltage? We will see what it is. Okay. So that is why V1 that we are giving primary voltage is always 230 volts 50 hertz AC. So if I draw the signal, it is something like this. With the peak to peak amplitude V1 equal to 230 volts and the frequency here it is 50 hertz. Right. So this is V1. Now with this voltage, what is that I see at the secondary end? This primary windings is inducing this voltage to the secondary. Since the number of turnings at the secondary end is less, so what happens to the voltage? The voltage scales down from 230 volts to a lower value. Okay, scales down from 230 volts to a lower value. And usually what we say is that voltage is around 18 volts or 15 volts based upon the number of windings that we give and based on the number of based on the voltage at power mains. Because sometimes you may have it as 220 volts, sometimes 230, sometimes 250, isn't it? So based on the primary voltage, the secondary voltage will be developed, but it is less when compared to primary voltage. Okay. So, and what is this primary voltage? That depends upon the relation between voltages and the turns ratio. V1 by V2 equal to N1 by N2. So from which what is that I have? V2 is equal to V1 into what is it? N2 by N1. So for example, if I take 230 volts, N1 is to N2, for example, it is say for our understanding, let us say it is 10 is to 1. So what happens? 230 into 1 by 10. So what do you think is this voltage here? It is 23 volts. So what you see, primary voltage is 230, secondary voltage is 23 volts. On what basis this voltage we obtain? Based on the turns ratio. Based on the turns ratio as well as the primary voltage. So in general, we go with 18 volts as the secondary voltage based on the primary voltage that is received from the AC mains. And whether it is 23 volts or 230 volts, it is for sure that this is also a sinusoidal signal. But only difference is with reduced amplitude. The amplitude is reduced. How much it is? 23 volts. And time period, this is important. Time period is nothing but reciprocal of frequency, right? Frequency is equal to 1 by time period. Frequency is equal to 1 by time period. So frequency doesn't get changed when the signal is induced from primary to secondary, which means the frequency at the secondary end, it is also 15 hertz. The frequency at the secondary end is also 15 hertz. This is one very, very important question. If primary voltage is got 230 volts, 50 hertz AC, what is the secondary voltage and its frequency? So remember, frequency will not change as we move from primary to secondary. Only amplitude gets affected. That too when the turns are differed. Okay. So this is what we see at the primary and at the secondary end. Now, as soon as you see the input voltage changing V1, accordingly I1 changes. And when I1 changes and some voltage is induced at the primary, because of the flux lines, that voltage is induced to the secondary. And immediately you observe the secondary voltage V2 available here. Okay. Now, what is that V2 that you see? It is also a sinusoidal signal, but with less amplitude. Yes or no? So this is what I see as V2. And here, this is what you see as V1. Now, for this input, how the diode is responding and accordingly, what is the output voltage V0? Okay. So what is that our input waveform I have shown? Our input waveform I have shown is a sinusoidal signal like this with omega t is what usually we show. What is the difference between t and omega t?
Frequency plus.
Omega t is angular time period. T is time period. Omega t is angular time period. Okay. So this is what you have as the primary voltage. Now, if you want to draw the secondary voltage, I can show the secondary voltage also with the sinusoidal signal. But what is the difference between primary and secondary with respect to the amplitude? Okay. So here I have the maximum value. For example, let us say 230 volts. Here it becomes 23 volts. Okay. And usually the general notation that we go here is Positive peak will be represented by plus Vm, negative peak will be represented by minus Vm. Okay, and it starts with the 0 positive half cycle and ends here. And what is this point where the positive half cycle ends? It is represented by pi. It is represented by pi, that is 180 degrees. Then negative half cycle extends from pi to 2 pi. Then if the waveform is repeated, the next positive half cycle extends up to 3 pi. Then negative half cycle extends up to 4 pi. Okay, so that means this one, which is what I am calling as a secondary voltage, is actually the input voltage to the diode. Yes or no? It is not V1 that is going as input to D. It is the secondary voltage which is going as input to the diode. So I can say V2 is equal to Vi. And we see that this input voltage has got continuous input. Fine, one positive, negative, positive, negative, positive, negative, and it continues so on. Fine. So for me to analyze this circuit for this type of input, so to what extent I can go for the analysis? It is enough that if you analyze this for 1/2 cycle, because you see that it is periodic. So again another positive negative. After that another positive negative. So instead of analyzing me the output for each and every half cycle present here, it is sufficient if I analyze this particular circuit for one positive half cycle and for one negative half cycle. So for one complete cycle, if you analyze this particular circuit and see what is the output, it is the same for all the remaining cycles. Is that clear? So we are going to take here the time period as one complete cycle because it is periodic in nature, shape is not getting changed. So periodic for every time period t. So here what is the time period t equal to? It is equal to 2 pi. Isn't it? For every period of 2 pi, the waveform is repeating itself. So that is how we define time period. Time period is the period for which the waveform repeat itself. So here the input waveform is repeating for every 2 pi period. So the time period for input signal is going to be t, which is equal to 2 pi. So with this as the input, we need to observe what is the final output that we get. So here on the same axis, we are plotting V0. So here this is V2, which is equal to Vi secondary voltage. Here it is V1, which is the primary voltage. Okay. Now how to analyze this output? To analyze this output, we said that take one complete cycle. Again, in one complete cycle, you have positive and negative half. So what you do is first analyze the input for 1/2 cycle. So what is that we do? We take first positive half cycle as input. So when I take positive half cycle as input, what is that I see? So you don't find any negative half cycle. Instead, you find just only one positive half cycle, which is existing for the period what? 0 to pi. Okay. So what is the positive half cycle as input? It is a cycle which is existing for the period 0 to pi. Okay. So now for this positive half cycle as input, what is the state of the diode? Anyone? It is forward bias. Why? And one more important thing that you need to remember is you are assuming that the diode is an ideal diode. So this is only just for our simple understanding. So we are assuming that the diode is an ideal diode. So there is no concept of V gamma. Okay. So when the diode is forward biased, immediately we can replace it with a short circuit. Fine. So now for positive half cycle as input that is existing for the period 0 to pi, we observe that the diode is forward biased. So now if the diode is forward biased, what is that we can replace it with by? Short circuit. So let me not show the primary voltage. This is only from the secondary and I'm showing because we are interested only in the secondary part here. So what is your voltage now? You have given plus minus, and this is the input you have given with the positive peak, which is equal to Vm, right? Okay. So this is, and let us analyze it for the maximum case, because if I analyze this for one case, it is the same for the remaining. So usually what we do is we take it for the maximum voltage case. So what happens now? For this positive voltage, diode is forward biased. So what happens? We see that current passes in the circuit. Okay. And not only this current passes, it also passes through RL. Let me say that current I have seen is I. So when this current I passes through RL, what happens to V naught? Is V naught existing or not? Do V naught exist? See, this is almost similar to a clipping operation. Current, when does it flow? When there is a closed path. So here there is a closed path. So current flows. When current flows, what is this output voltage V naught?
IRL.
Yes, that's all. I into RL.
RL.
Okay, current V naught is equal to I into RL. Now, final thing is, what is the magnitude of this V naught and how do I show it here in the output? That is important. So to know that, first you should decide on what parameter this V naught is depending. So to understand clearly, this is load resistance and current passing through RL. These are the only two parameters upon which V naught depends. So now, can I say that V naught is depending on RL? That means V naught changes as how RL gets changed. Yes, no. So we can.
Load resistor constant.
Yes, that's what I'm expecting. So load resistance is fixed. So when you're designing a rectifier circuit, you take resistance, let us say, for example, 1 kilo ohm. So 1 kilo ohm, it doesn't change throughout the operation of the rectifier. Okay. So V naught is not depending on RL. Instead, V naught depends on what? I. Where I is what? Current passing through the circuit. Now the question is, on what parameter this I depends? When is current passing in the circuit? Yes, when current started to flow in the secondary part. No one. When current started to flow in the circuit. Usually when current flows in a circuit. Not audible, ma.
Ma. Ma.
When does current flows in a circuit? Nobody. Varlakshmi, your voice is not audible. See, you have a circuit like this.
P2.
V is 0. Will current flow?
No, ma'am.
What is I?
0, ma'am.
0. Now let us say V, I have given 10 volts. Do you think current flows?
Yes, ma'am.
Means when current is flowing in the circuit?
When voltage exists, ma'am.
When voltage is applied. Isn't it? Only when you apply the voltage, current flows. Yes or no? Likewise, here I said that V naught is depending on I. But when I is appeared to see here in the circuit,
V in.
V in is given. What is V in this case?
23 volts.
Positive half cycle. V in this case is positive half cycle. So what is that I see now? This current I which is flowing in the circuit, this current I which is flowing in the circuit is the result of input voltage being available at the transformer. Now, is your input voltage constant? Because it is a sinusoidal signal, It is continuously changing with time. It is a sinusoidal signal which is continuously changing with time. Okay. So when Vn is changing with time, what do you comment on I?
Also changes, ma'am.
Also changes. In what way? According to Vn, isn't it? So that means if your input is starting from 0, okay, and going to maximum value, you see that current here also starts from 0. Let me plot here I, for example. What happens for the positive half cycle? If I extend this onto x-axis, so for positive half cycle, it starts from 0, and then as how input is changing, it also increases, goes to the maximum value, and then slowly as input is decreasing, current also decreases. So that is what I mean. V not depending on I, further I is depending on Vn. But finally, what is important for me? I want what is the output voltage V naught. What is output voltage V naught? I said it is equal to I into RL, right? Now my I is depending on input. When input is having maximum value Vm, current here also has the maximum value Im. Now this I is passing through RL and is developing what? V naught. So what do you think is now the output voltage waveform?
Positive cycle. Positive
So
cycle.
it depends on how Im is changing. So which means it starts from 0, goes to the maximum value, and again comes to 0. Okay, so what is the voltage here? It is also going to be Vm. Pm. So for this applied input, positive half cycle, current passing through the diode is this, and final output voltage available is this. So in few textbooks, they don't show this intermediate waveforms. They show directly the input and they show directly the output. But how you got the output from the input? In between is this part which you need to understand clearly. Okay. So finally, I see that V naught simply follows the input Vn, because RL is fixed and V naught is depending on I, and I in turn depends on the applied input voltage. So what is that I understand? For positive half cycle as input for the period 0 to pi. What is that I see? I see the output also exists for the same period 0 to pi. Any doubts in this? Clear?
Clear, ma'am.
Then let us move on to the next part. That is for the negative half cycle as input. So negative half cycle extends for which period? Negative half cycle.
5 to 2 pi, ma'am.
Yes. Why I'm mentioning these periods later you will understand. Okay, so your negative half cycle is available for the period 5 to 2 pi. So for this negative half cycle as input, what is the state of the diode? To understand that, I need to go to the circuit. So now I am giving input is the negative half cycle here, the one with blue color, pi 2 pi. Okay, so now once this negative voltage is received to the diode anode, what happens to the state of the diode?
Reverse bias, ma'am.
Yes, diode becomes reverse bias. So when diode is reverse bias, what is the equivalent circuit?
Open circuit, ma'am.
Yes, so there is no closed path here. It is an open circuit. Now what about the polarities of voltages here? Negative voltage, so minus, plus, and I show here the maximum case. Even though your input is changing, starting from 0, slowly going to negative voltage and then coming back to 0, to show here for our easy understanding, we take the maximum case. So this is it, minus Vm. This is minus Vm. Okay, so minus plus. Diode is open circuit. So what is finally the current passing through the circuit I?
0, ma'am.
I is 0. If I is 0, what is V naught?
0, ma'am.
V naught is 0 volts. So that means for negative half cycle, what is that we see?
No voltage and no.
So V naught is I into RL. RL is fixed, but what is that I see here? Current is 0. So automatically I see that V naught is equal to 0 volts. V naught is equal to 0 volts. So if I plot this here in the waveform, this is for me the period of negative half cycle, right? So I said current I is 0. So no current. Now when current I is 0, this expression did not change. V naught is equal to I into RL. But what happened in the negative half cycle since this I has become 0, automatically V naught turns out to be
0.
0. So the output here is going to be just like this. Now if your waveform is repetitive, what do you think is the next output here?
Positive cycle.
Positive half cycle. Follows output like this. Then negative half cycle,
0, ma'am. B.
0. Finally, 0. So this is how you see the output waveform for this. Now, if you see your input cycle has got both the half cycles, right? Your input has both positive half cycle as well as negative half cycle. But what is that you see in the final output waveform?
Positive half cycle.
You see the presence of only positive half cycle. What happened to negative half cycle?
It will be.
It got clipped, isn't it? That's the reason why you are calling this as a half wave rectifier based on the output wave shape. Okay, based on the output wave shape. The classification that we have given for the rectifiers is half wave and full wave. Is half wave and full wave. So here in half wave rectifier, for the complete cycle as input, output is only one half cycle. Now here I got positive half. For example, I want to have only negative half cycle in my rectifier operation. So what should be the circuit change?
Diode reverse.
Diode should be reverse biased. So if this diode is reverse biased, you get an output which is like this. So what is that I see? No negative half, no positive half cycle. Like this. When the diode in the circuit is reverse biased like this. Okay. So this is how you have the operation of a half wave rectifier. So this is what we call as input, output waveforms. Input, output waveforms. Clear? So for any rectifier circuit, this is what we will be studying. First one we study is the circuit. Second one we study is the operation. Third one we study is the input, output waveforms. Clear? Any doubts in this? So your final output here is going to be this.